Hey guys, so we left off at the bottom of page 7 of the notes, and I was about to tell you about this technique that we can use to solve equilibrium problems and make predictions about equilibrium using a technique called the icebox, I-C-E box. And we can use the icebox in sort of two different situations. We can use it to either A, solve for K, the value of K, the equilibrium constant, if we're given initial conditions and at least one equilibrium condition, or we can use it to solve for equilibrium conditions or concentrations. That's sloppy. Let's try that again. Equilibrium concentrations if we are given initial conditions and the value of K already. So what does ICE in icebox stand for? I stands for initial. C stands for change. And E stands for equilibrium. All right, so we set up this sort of table where we record the initial concentrations, the change in concentration, and then the equilibrium concentration. So the change, if the substance is going down, like in the case of a forward reaction, the reactants will go down. So in a forward reaction, the amount of the reactants goes down and the amount of the products goes up. So if it's going down, then it would have a negative sign, and the change would be negative. If it's going up, like in the case of the products here, it would have a positive value, right? And the equilibrium is just the initial minus the change, or I guess initial plus the change. If the change is negative, if it's going down, then it would be initial minus the change. And if the change is positive, if it's going up, it will be initial plus the change. Okay, so let's sort of see this in action here. We'll start with an example. All right, this is some example problems where we're solving for K. We're using it for that first technique. So we've got a reaction. A reacts to form 2B. And we're given an initial concentration of A and told that there is no B. And at equilibrium, the concentration of A, we're given a concentration. What's the equilibrium concentration of B, and what is the value of K? So I like to set up the icebox by first just rewriting out the equation. So we've got A reacts to form 2B. And, oh shoot, I can hear my phone ringing downstairs, but I'm not going to answer it. So I sort of turn this into columns, all right? I, C, E. Okay. I is initial, so the initial concentration of A, it tells us, is 1.00 molar, and it tells us there is no B, so we can put a 0 there. Then it tells us the equilibrium concentration of A is 0.75 molar, so we plug that into the equilibrium line of this table. And then that's it. Then it says, what is the equilibrium concentration of B? And also, what is the value of K? All right, so those are the things we're trying to find. Well, let's start with the table, all right? If we know two values in a column, we can solve for the third, because equilibrium is just the sum of the initial and change. So if we initially had 1 molar, and we, at the end, at equilibrium, had 0.75, that means we went down by 0.25 molar, all right? And from the stoichiometry here, for every 1 A, we make 2 B. So if A went down by 0.25, then B went up by 2 times 0.25, which is by 0.5 molar. Okay, so if we started at 0 and went up by 0.5 molar, then the concentration of B at equilibrium is 0.5 molar. So we solved for the concentration of B at equilibrium. Great. Okay, K, we don't know the value of it, but we do know that we can write the expression, which is B squared over A. all right? And these are concentrations at equilibrium. This is the equilibrium constant. So these concentrations that we plug in are not going to be the initial concentrations. It's going to be these equilibrium concentrations that we're plugging in here to solve for K. All right, so K equals the concentration of B at equilibrium, which we've solved is 0.5 molar, squared, divided by the concentration of A at equilibrium, which we are told is 0.75 molar. So the value of K that we solve for is simply 0.33. All right, so the ice box is simply an organizational tool to help you go from initial conditions to equilibrium conditions using that, calculating that change. All right, and then we can use those equilibrium concentrations that we find using the ice box and plug them into our equilibrium constant expression to solve for K. All right, let's try it again. All right, here's another example problem. At 780 degrees Celsius, the concentration of carbon monoxide, and here's our equation down here. All right, and I'm just going to turn this equation, if you're doing this problem from like the book or online from Sapling, write it on your page and just turn it into a table. Okay, so here's I, C, and E. Erase the remainders. Okay, so initially it says that we have 0.5 molar of carbon monoxide. And I'm just abbreviating my sig figs because of space here. And for the H2, we have 1.00 molar. All right, and so we're not given a value of methanol, so we can assume that we don't have any of that initially. All right, notice that although we have some coefficients here, all right, we don't use that to adjust the initial concentrations. The concentrations are what they are. Coefficients be damned, okay? The change, that is where the coefficients become important, all right? So coefficients are important for this row of the table only, okay? But we can't put this in yet because we're missing one piece of information, which is that at equilibrium, the concentration of CO is 0.15 molar. Okay, so now we filled in everything we have for the table. We want to know what is the value of K. That's what we're trying to solve. But first, we need to fill out the table because in order to solve for the value of K, we need the equilibrium concentrations. So we can start here in this first change. If carbon monoxide starts at 0.5 molar and ends up at 0.15 molar, then that's a change of negative 0.35 molar. And since hydrogen has a 2 in front, it's going to go down, I'll say negative, by 2 times as much. So 2 times 0.35 molar. And the methanol will go up by 0.35 molar. So the new the equilibrium concentration for the methanol is just going to be 0 plus 0.35. And the equilibrium concentration of the hydrogen is going to be 1 minus, and I'll do this to the side, 1 minus 2 times 0.35, which is 0.7. So that will be 0.30. So 0.30 molar. Okay, I'm going to erase my little math over here on the side. Alrighty, so now we have equilibrium concentrations that we can plug into our equilibrium constant expression. And maybe we should write that out. Erase this question mark for a second and write out that for this equation, CH3OH is the product and the reactants, concentration of the reactants on the bottom here, H2 is squared. Alrighty, so now we just plug in these values. K at equilibrium, the concentration of the methanol is 0.35 molar, as we see in our table. And the concentration of the carbon monoxide is 0.15 molar. We were given that one. And the concentration of H2 is 0.3 molar. We calculate that, and we need to remember that squared because of the 2 in the equation. We plug that into our calculator, and we get that K equals 26. All right, I only have 2 sig figs in this value, so my answer is only going to have 2 sig figs. So the K equals 26, and we figured that out first by making an icebox so that we could solve for the equilibrium concentrations of everything, and then we plug those equilibrium concentrations into our expression for the equilibrium constant. All right, the next page has a problem for you to try. Feel free to pause the video here and try this one yourself. It uses the same equation from the previous page. So I'm just going to rewrite it out. Carbon monoxide plus 2 moles of hydrogen gas react to form 1 mole of methanol, CH3OH. And I'm going to turn this equation sort of into a table. That is my icebox. All right, so the concentration initially of CO, it tells me, is 0.27 molar. And the initial concentration of hydrogen gas is 0.49 molar. And I don't have an initial concentration of the methanol, but I do have an equilibrium concentration of the methanol. So I'll plug that in right here. All right, so similar problem, instead we're given the equilibrium concentration of the product instead of the equilibrium concentration of one of the reactants. Either way, if we have a column with 2 components filled in, we can solve for the third. So if it went from 0 to 0.11 molar, that means it went up. The change was positive 0.11 molar. And since the change is related stoichiometrically, all right, the change, since this has a coefficient of 1 and the carbon monoxide also has a coefficient of 1, for every 1 methanol we make, we lose 1 carbon monoxide. So it went down by 0.11 molar. And the hydrogen went down by twice that much, 2 times 0.11, which is 0.22 molar. Now we just do some subtraction or addition, however you want to think of it. 0.49 minus 0.22 is 0.27 molar. That's our equilibrium concentration. And over here, 0.27 minus 0.11 is 0.16 molar. So now this is the part of the table that we care about. That's what we were trying to solve for so that we can plug it into an equilibrium constant expression. So remember, for this equation, products, CH3OH over concentration of reactants, H2 squared because of the 2 coefficient. So K equals, and I'll go with these equilibrium values, plug in these equilibrium values, 0.11 molar divided by, so the equilibrium concentration of carbon monoxide is 0.16 molar, and the concentration of hydrogen at equilibrium is 0.27 molar. Square that one and type it all into our calculator, and the answer is 9.4. Remember, K does not have units, and in this problem we're given 2 sig figs in all of our values, so our answer needs to be 2 sig figs. All right, so that's the first method of using the icebox to figure out the rest of the equilibrium concentrations when you're given 1 to start with, and then you can plug those into the equilibrium expression and solve for K. A second sort of technique for using these ice boxes is to solve for equilibrium concentrations when you're not given any of them, but you are given the K value. All right, so we're going to move through this problem in a stepwise fashion. Still, we're given an equation. Nitrogen plus oxygen reacts to form 2 nitrogen monoxides. And it gives us initial concentrations. Initially, we have 0.2 molar of the nitrogen and 0.2 molar of the oxygen. And it says find the equilibrium concentrations of all species. All species just means all of the different compounds in the reaction. So the first thing we need to do is determine which way the reaction will go. Now, in this circumstance, it's pretty obvious. We're only given amounts of reactants. We don't have any product. So the only direction for this reaction to go is forward. There's no product to go in the reverse direction. So obviously, if you're just given reactant, you're going to go in the forward direction. So then the second step is to create our icebox. Okay, so we figured out step 1. It's going in the forward direction. Step 2, let's create our icebox. So we've got N2 plus O2 reacts to form 2NO. And I'm just going to turn this into a table, columns, I, C, E, initial change equilibrium. Initially, we have 0.200 molar and 0.200 molar of this. I'm just leaving out those extra zeros for space, but don't forget that we have 3 sig figs in this problem. And initially, we don't have any nitrogen monoxide. All right, that's all we're given here. We are not given any of these equilibrium constants, so we can't know the value of the change. But we can use X for the change. All right, that's what we're going to do. So we're going to plug in X as a variable to indicate the change. So in other words, the nitrogen gas is going to go down by some value of X. The oxygen will also go down by that same value of X. And according to the stoichiometry, the nitrogen monoxide is going to go up by twice that value of X because of that 2 coefficient. So we can say that at equilibrium, the nitrogen will have a concentration of 0.2 minus X, and the oxygen will have a concentration of 0.2 minus X, and the nitrogen monoxide will have a concentration of 2X, all right? And we can plug those in to the equilibrium constant expression and solve for X because we're given the value of K. So let me just write out as a reminder the equilibrium constant expression for this reaction will look like this. All right, we're given the value of K in the problem. K is 0.10, and we can plug in our values of NO from the table here. The equilibrium constant, the equilibrium concentration is 2X, and we need to square that. And then on the bottom here, the concentration of N2 is 0.2 minus X, and the concentration of O2 is 0.2 minus X, all right? Another way to write that is 0.2 minus X squared. And when we write it that way, it's a lot easier to see how we're going to solve this, because the first thing we can do is take the square root of both sides of that equation to get rid of that 2 exponent. The square root of 0.10 is, looking up my math, 0.316, 0.316, and the square root of this side of the equation is just now 2x over 0.2 minus x. All right, the next thing I need to do is multiply both sides by 0.2 minus x, and that'll cancel out on this side. And I'm going to need to distribute this. So I will get 0.2 times 0.316 is 0.0632 minus 0.316x equals 2x. Now I need to move the x's over to one side of the equation, so I'm going to add 0.316x to both sides. And this cancels out, and we get 0. I'm gonna get 0.0632 equals 2.316x, and now I just need to divide both sides by 2.316. 316. And I get x equals 0.027. All right, I'm not done with this problem. All right, the last step, step 4, is to plug in x in each of these places so I can solve for the equilibrium concentrations of each. So there's room on the next page for you to write out the final answers if you want to move on to page 10. I'm going to try to write them over here. So at equilibrium, all right, the concentration of N2 is 0.2 minus x, x is 0.27, sorry, 0.027, and this is molar, it's a concentration. So we get a concentration of 0.173 molar at equilibrium for the nitrogen. And for oxygen, it's going to be the same, all right, because it's still 0.2 minus 0.027. So it's also going to be 0.173 molar. And the concentration at equilibrium of the nitrogen monoxide, the NO, is simply 2x, or 2 times 0.027, which is 0.054 molar. All right, and that's the answer. In sapling, you'll have a question like this, and it'll probably give you answer boxes for each of these. So you'll have to figure out, you've got to use the ice box, plug in x for the change, and then use the equilibrium constant expression to solve for x. And then lastly, remember to come back and do those subtraction or multiplication problems to solve for those equilibrium concentrations. All right, that was just example number 1. We still got 2 more to go. So on to page 10. All right, same reaction, different temperature. And at a different temperature, we have a different value of K. Also, we're given different initial conditions. And this time, initially, we have given a concentration of NO. So let's rewrite out this equation from the previous page. N2 plus O2 reacts to form 2NO. All right, and initially, we set up our ice box, I, C, E. All right, initially we are given an amount of the nitrogen monoxide, 0.0100 molar. All right, no mention of reactants. All right, so in this case we're starting with product and we have no reactant. So this is an obvious case where the reaction is going to be going in reverse. All right, and when the reaction is going in reverse, the product is not going up, it's going down. So this change of 2x is going to be negative. And the change in the reactants, these x's are going to be positive because the reactants are going to increase since we're going in the reverse reaction. Okay, so then we can plug in for the equilibrium concentration of each of these is 0 plus x is x, 0 plus x is x, and 0.0100 minus 2x is the equilibrium concentration for the NO. All right, the equilibrium expression for this equation is still the concentration of the product squared divided by the concentration of each of the reactants. All right, and we're given this value of K. It's 0.005. So we're going to use that value of K and these equilibrium concentrations from our icebox, and we're going to plug it in. So we've got K is 0.055, and the equilibrium concentrations from the table for NO, it's 0.01 minus 2x squared divided by x times x. Or another way to write that is x squared. All right, so again, solving it the same way, take the square root of both sides. The square root of 0.055 is 0.235 equals 0.005. 0.01 minus 2x over x, right? I'm going to multiply both sides by x. So basically I'm moving x over to this side of the equation. Try to do some erasing here. All right, now I need to move all the x's to one side, so I'm going to add 2x to both sides. Cancels out over here, and I get 2.235x equals 0.01. Now I need to divide both sides by 2.235. And I get that x equals 0.0045. All right, ultimately we want to know what are the equilibrium concentrations of everything, and now we can write that. The equilibrium concentration of N2 is just equal to x, which we just solved to be 0.0045 molar, it's a concentration. For O2, it's also just equal to x. And then for the concentration of NO, it's equal to 0.0100 minus 2x, and x is 0.0045. So that equals 0.001 molar. Okay, so those are the final answers, the final concentrations. Once equilibrium is reached, these are the concentrations of each of the species here in this reaction. All right, third and final problem. Same reaction, different temperature, different K, and different initial conditions. So we'll write out our formula. N2 plus O2 reacts to form 2NO. And we'll make our icebox, ICE, for each of these species, I guess I'll say. All right, so it says initially we have 0.75 molar of N2, 0.75 molar of O2, and 0.45 molar of NO. All right, we can do the change, the X's, except we don't know which direction this reaction is going in. Is it going forward or we reverse? We don't know. It's not obvious because we have a little bit of product and we have a little bit of reactant. So for this one, the first thing we need to do, we need to answer this. Which way is the reaction going? To do that, we need to find Q. All right, in other words, plug in these into our sort of our reaction quotient equation, which is just NO 0.45 squared. So this is the same thing as K. It's sort of the same setup as K. So the product squared divided by the reactants, 0.75 times 0.75. All right, and we get that Q equals 0.36. All right, if K, so K is 0.08 and Q is 0.36. Q is greater than K, which means it's going to go in the reverse direction. All right, so we're going in reverse. If we're going in reverse, that means we're subtracting product and we're adding reactant, or that the reactant will go up and the product will go down. I have 1 minute left. Okay, so our equilibrium concentration is going to be 0.75 plus x, 0.75 plus x, and 0.45 minus 2x, right? We are given the value of K. K is 0.080, and we plug in these equilibrium concentrations, 0.45 minus 2x squared, and 0.75 plus x squared, and we solve for x. which I'll show you the answer in the next video.